Real-time AI isn't just about raw model capability. It's about the milliseconds between a user's request and the first token they see. For voice assistants, coding copilots, and live recommendation engines, latency is the product. A model generating tokens at 10 per second feels broken. One hitting 80 plus tokens per second with a sub 100 millisecond first token feels instant. There are two metrics every ML infrastructure engineer needs to internalize. First, time to first token, how long from request submission to the first generated word. This drives perceived responsiveness and is dominated by per-fill computation. Second, intertoken latency, the gap between successive tokens during generation. This determines how smooth streaming feels. And behind both of these sits throughput, total tokens per second across all concurrent requests, which ultimately determines your GPU cost per million tokens served. The problem is that latency and throughput pull in opposite directions. Small batches reduce latency, but kill GPU utilization. Large batches maximize throughput, but introduce queuing delays. The 16 techniques in this engineering playbook give you the tools to navigate that trade-off, and when stacked correctly, they compound to 5 to 10 times combined performance gains. Let's start with streaming and parallelism. Streaming generation is the prerequisite for everything else. Transmit each token to the client as it's generated rather than buffering the full response. A reply that starts appearing in 150 milliseconds feels dramatically more responsive than one that delivers 500 tokens after a 3-second wait, even if the total generation time is similar. Implement this via server-sent events or chunked HTTP. It's the OpenAI API's default behavior, and your users will notice immediately. Token parallelism splits model weights across multiple GPUs, so a single forward pass uses all available compute simultaneously. Tensor parallelism at degree 4 reduces per token latency by roughly 33% on NV-link-connected H100 systems. Async per-fill takes this further by disaggregating the prompt processing phase from token generation onto separate compute resources. Systems like Mooncake have demonstrated 2 to 3 times throughput improvements at scale. Now let's talk memory systems, where some of the biggest wins lie. PagedAttention, introduced by the VLLM project, is arguably the single most impactful algorithmic contribution to LLM serving in recent years. Traditional serving frameworks allocated contiguous GPU memory for each request's KV cache at the maximum possible sequence length, wasting 60 to 80% of that memory through fragmentation and overprovisioning. PagedAttention borrows virtual memory paging from operating systems. KV cache blocks are managed non-contiguously via block table, eliminating both internal and external fragmentation. The result, VLLM achieves under 4% KV cache memory waste, down from that 60 to 80% figure. This directly enables larger effective batch sizes and dramatically higher GPU utilization, with no changes to the model itself. KV cache quantization complements PagedAttention by reducing the memory footprint of stored keys and values. Storing them in INT8 instead of FP16 halves the memory usage. INT4 reduces it by 4 times. For a 70 billion parameter model serving 100 concurrent requests, this can mean the difference between fitting on 2 GPUs versus 4. On the hardware side, CUDA graphs are a near-free optimization that every production deployment should enable. Each PyTorch operation normally triggers a separate CUDA kernel launch from the CPU. For the decode phase, where you're generating one token at a time, this launch overhead can dominate actual compute time. CUDA graphs record the full sequence of GPU operations once, then replay the captured graph as a single operation on every subsequent call. Fireworks AI measured this, delivering a 2.3 times speedup on LLaMA7B, entirely from eliminating CPU overhead. FP8 kernels on H100 GPUs take hardware acceleration even further. NVIDIA's TensorRT LLM benchmarks show H100 FP8 achieving 4.6 times the maximum throughput of A100 FP16. That's not a small gap. That's a generational leap. Bassetten's production data confirms 33% faster inference at batch size 128 with under 0.5% accuracy degradation. Continuous batching is the most important batching innovation for LLM serving. Traditional static batching holds GPU resources until every request in a batch finishes, which means the GPU sits idle waiting for the longest sequence, while short requests have already completed. Continuous batching rebuilds the active batch after every single decode step, immediately slotting in new requests as others complete. Combined with PagedAttention, VLLM demonstrated 23 times throughput improvement over naive Hugging Face serving. If you're not running continuous batching, this is your highest leverage starting point. Speculative decoding is the most theoretically elegant technique in the playbook. A small draft model predicts 3 to 5 tokens ahead. The full target model verifies them in a single forward pass. If the draft tokens are accepted, you've generated multiple tokens for the cost of one. The output distribution is provably identical to standard sampling. Snowflake suffix decoding variant achieves 2.3 to 6.3 times latency reduction on coding workloads, the best real-world numbers for any single inference algorithm. For implementation priority, start with Tier 1, deploy VLLM or SGLang, which gives you continuous batching and PagedAttention in one move. Then enable CUDA graphs, add FP8 if you're on H100, and turn on streaming. That stack alone often delivers 10 to 20 times throughput improvement. Move to Tier 2 for KV cache quantization and prefix caching. Add speculative decoding in Tier 3 when you have a quality draft model available. The gap between a tuned serving setup and an untuned one is larger than the gap between H100 and A100 hardware. Optimization pays more than hardware upgrades, and these 16 techniques are the playbook. Read the full engineering playbook at ThinkSmart. Life/research/posts/